Okay, so we were talking about lumped capacitance method. So let me briefly explain what it is. So when we have a transient heat conduction, that means that the temperature is going to change in time. So the temperature is going to change in time and space. So it depends on the location in the system and the time. So the temperature is going to be a function of space, x, y, z, and time t. So the governing equation is going to be partial t squared over partial x squared is going to be 1 over alpha, which is the material property, times partial t over partial time. So we have a second order partial differential equation in space and first order differential equation in time. So this one looks pretty complicated. So what we are going to do is we are going to find a unique heat transfer problem where we can neglect temperature change in space. So when that happens, if we have a solid object in a fluid, when we have fluid at a temperature T infinite, and let's assume that the amount of fluid is much larger than mass of the solid, then we can assume that the temperature of the fluid is going to be uniform. So it's going to be T infinite. The temperature of the fluid is uniform, while the temperature of the solid is going to change. So the temperature of the interest in this problem is going to be how this temperature of the solid is going to change. In reality, when there is a heat transfer from the solid to the surrounding fluid, or the other way, from the fluid to the solid, which is the same question, let's assume that there is a temperature, there is a heat transfer from the solid to the surrounding. Then let's see what happens. Initially, Ti, the initial temperature is 100 degrees Celsius, and the temperature of this surrounding fluid is going to be at 20 degrees Celsius. Because the temperature of the solid is greater than the temperature of the fluid, there is a heat transfer from the solid to the surroundings. Because of that, the temperature of the solid is going to decrease from 100 down to 80, 60, 40, and eventually, a long time later, the temperature of the solid is going to be 20 degrees Celsius, the same as the surrounding fluid. That's when we say they are in thermal equilibrium. Then our question is that how fast this temperature is going to change. And there are two different the cases. If the thermal conductivity, if the conduction heat transfer in the solid is excellent, then there should be almost no temperature difference between the core of this solid and the surface of the solid. So let's say after maybe sometime later, the temperature of the solid is going to be, let's say, near 80 degrees Celsius, and the temperature near the surface is going to be close to 80, maybe 75, because the heat transfer within this solid is good. Therefore, there is almost no the temperature difference between the center of the solid and the surface of the solid. On the other hand, we can have another solid whose conduction heat transfer in the solid is not that good. Then there should be significant temperature difference between the center of the solid and the surface of the solid. So in that case, instead of 80-75, we can say center is still near 100 degrees Celsius, let's say 95, but the surface is going to be at much lower temperature because the heat transfer from the surface to the surroundings. So we can say that the surface is going to be maybe the 60. If this is the case, we need to consider temperature distribution, the temperature gradient within the solid. That means we need the left-hand side of this equation because there is a significant temperature change. But if this is the case, we can assume that the temperature of the solid is uniform regardless of the location. The center is almost 80. The surface is not too far, 75. So you can say that the temperature of the solid uniformly decreases, 80, 70, 60, 50. Then do we need to worry about any temperature change between the core and the surface? Not really, because there's almost no temperature difference between the core and the surface. In that case, you can neglect the left-hand side. This is lumped system. So this red is lumped system. So if you see a transient heat conduction problem like that, we can use lumped method to solve their temperature change. If that's not the case, when there is a significant temperature gradient within the solid, then we need to consider the left-hand side of this equation. It means that our solution is going to be very complicated. So we are not going to use the exact solution. Instead, we are going to rely on approximate solution. So in this chapter 5, we are going to study how to, how to do lumped system analysis. That's the first one. And later, the other half is going to be how to solve by this approximate method. That's what we are going to do. So let's say that we have a lumped system. Then how can we solve it? This temperature of the solid is not going to be a function of x and t anymore. If you have a lumped system, the temperature of the solid is going to be just a function of time t, because we don't care about where it is, because we can assume that they're almost uniform. Okay? Then if we say that temperature is only a function of time, can we make a governing equation? Yes, we can. So we are going to see how we can, come up with the governing equation for this lumped system analysis. So that's what we are going to do. Our assumption is we have a solid and there's a heat transfer from the solid to the surrounding fluid. So there's a Q. And we want to know, and when the temperature of the surrounding is going to be T infinite, which is constant, and the temperature of the solid is going to be a function of time. Then there is a heat transfer by convection from the surface to the surrounding. So this heat transfer Q is going to be convection heat transfer. And how can you determine this convection heat transfer? By convective heat transfer coefficient H times the surface area A times the temperature difference. Okay. Then this is what happens when we have a lumped system, because we don't care about how the temperature is distributed in the solid, because we assume that it is uniform. When I say 80 degrees Celsius, the center of the solid is 80, the surface of the solid is 80. When I say the solid is 70 degrees Celsius, the center of the solid is 70, the surface of the solid is 70. So you don't need to worry about temperature gradients inside. You just need to, you can just assume that the surface temperature of the solid is the same as the entire temperature of the solid. That is the lumped system. Then let's solve this one by using energy balance equation. So what is the energy balance equation? Energy transfer in minus energy transfer out is going to be the change of energy of a system. Then what kind of energy transfer do we have? We have a heat transfer, Q, that goes out. So it will be E out. But Q is not E out. Q is the rate of heat transfer. It's not just energy transfer. This is the rate of energy transfer. So how can you determine the rate of energy transfer in this energy balance equation? We can divide by time. So instead of E out, we can say the rate of energy transfer out of the system, the rate of energy transfer into the system is going to be this solid, and the right-hand side is going to be the change of energy of a system per time. Then, what is the energy transfer into this solid? There is no energy transfer into the solid. There's only one energy transfer, which is from the solid to the surroundings, which is the convection heat transfer. So in this energy balance equation, you can neglect energy transfer in. We only have energy transfer out per time, which is convection heat transfer coefficient times area of the surface times temperature difference. Then, how can we determine the change of energy of a system? How do we determine the change of energy of a system? The change of energy of a system can be determined by the total energy at the final state minus the total energy at the initial state. What is the total energy? It can be mass times specific total energy per unit mass minus the total energy per unit mass at the initial state. How do we determine this lowercase e? It can be U2 plus kinetic energy and potential energy minus U1 plus minus kinetic energy and potential energy. That's what we studied in thermodynamics, right? Then, is there kinetic energy change or potential energy change? Not really. So you can neglect kinetic energy change and potential energy change. Then what do we have? We only have mass times U2 minus U1. And do you remember how to determine U2 minus U1? When we have a solid, we can use specific heat. Mass times specific heat times temperature difference, T2 minus T1. In other words, mass times specific heat times delta T, the change in temperature. So that's how we determine delta E, the change in the energy of the system. So we can replace this one with mass times specific heat times delta T. So this one is going to replace this. Then what is the equation? This equation becomes minus HA, the surface area, A of S, times delta T, temperature difference, is going to be mass times specific heat times delta T divided by delta time, the change in time. So this is our governing equation. But this delta T and this delta T, they are not the same. This delta T is the temperature difference between the solid and the surrounding fluid. So this is going to be minus HAS times temperature difference, T of the solid minus the surrounding fluid, T infinite, is going to be mass times specific heat times delta T over delta T, delta temperature over delta time. To solve this one, we can use this one in a differential form. What is the differential form of this one? D temperature over D time. So this is the differential equation we are going to solve to get the governing equation for the lumped system analysis. So let's do that. So can you solve it? As is? Not really, because we have a dt, we have a t, but we have a t infinite. So because of this, we cannot solve it as is. So we are going to replace this t minus t infinite with theta. I'm going to say theta is t minus t infinite. Then what is the first derivative of this theta with respect to time? D theta over dt is going to be dt over dt minus dt infinite over d time. Then what is this T infinite? That's the temperature of the fluid, which is constant. So dt, the change in constant, is 0. So d theta over dt is going to be d temperature over d time. So we can replace the right-hand side with d theta over dt. So this equation becomes minus h times the surface area times t minus t infinite, which is theta, is mass times specific heat times dt, d temperature over d time is going to be d theta over dt. Now, can you integrate them? With one condition, you can integrate them. What is that condition? This one is constant. This one is constant. This one is constant. Specific heat is constant. Then we only have two variables, theta and t. You can move t to one side. You can move theta to the other side and integrate them. That's how you solve this problem. So we have a t here. We can move this one to the left-hand side. We have a theta here. Move this one to the right-hand side. Let's put all the constants to the right-hand side. Let's move them to the right-hand side. Then what is the governing equation? We get d theta over theta is minus HA over mass times specific heat. By the way, there's one thing. By the way, you know that we prefer density times volume rather than mass, you will know it's going to be convenient later. So instead of mass, you can say density times volume. Then at the bottom, we have a density times volume times specific heat C times, we have a dt, go to the left-hand side, dt. Now, can you integrate them? Yeah. So let's integrate. What is the left-hand side? Minus HA rho VC. They are all constants. So we can just say HA over rho VC. There's nothing wrong because they are constant. We have a dt. The integration of dt is going to be just temperature at t, at time t. And what is the integration of d theta over theta? Integral dx over x is going to be natural log x. So we can say natural log theta. Then, do you think that this one looks okay? Not really. We want to, put this theta on one side and put everything on the other side because we are interested in theta, which is temperature. So let's do that. Natural log A is B. That means A is e to the power B, right? So theta is A. Theta is going to be E2 minus HA over rho VCT. So this is the governing equation. However, when you integrate, we get an unknown constant. So that unknown constant should be somewhere. So I'm going to add that unknown constant C here. That's not the specific heat. It's unknown constant C after you integrate this equation. Then, can you determine C? Yeah, there's one way. What about if I know the initial temperature T of the solid when time is 0? So T is Ti, the initial temperature at time T is 0. Then we said T minus T infinity is theta. So I'm going to replace this one with theta. So this equation becomes theta is theta I. By the way, theta I is Ti minus T infinite. It is at temperature T is 0. So this is the boundary condition, not boundary condition, initial condition to determine C. Then let's substitute this 0 for T and theta I for theta. Then what do we get? Theta I is unknown constant C times E2 minus HA over rho VC T, but T is going to be what? 0. Then what is E2 0? 1. So this unknown C is going to be theta I. So let me rewrite this equation. Theta is going to be theta I times E2 minus HA over rho VCT. Oh, wait, we have a theta on the left-hand side. We have a theta on the right-hand side. Let's move theta, every theta to the left-hand side. Can we do that? Yes, divide by theta I. Divide by theta I. Then what is the governing equation? Now there's a governing equation. Theta over theta I is going to be E2 minus HA over rho VCT. And what is theta? Theta is T minus T infinite. And what is theta I? Ti minus T infinite. Ti minus T infinite. So this is the governing equation for the lumped system. Then Can you solve this equation? Yeah. Hmm? Wait, this one? We'll see. E, that's a minus HA over rho VC. They're all constant times temperature, times time. So this one, this will looks much clear right now. Yeah, that's the governing equation. So whenever you have a lumped system, whenever you have a transient heat conduction problem, the governing differential equation looks extremely complicated. And solving this one looks a lot of headache, right? But if you can assume that your system is a lumped system, the solution to this complicated second order partial differential equation is going to be this simple. Then what is the variables here? If you know time t, you determine the temperature of the solid. Okay? So if you know time t, you can determine what is the temperature at this time t of the solid. Or if you know the temperature of the solid, you can calculate how long did it take to get this temperature. Okay? Any question? Then you should have one more question, one last question, which is, okay, so if I have a lumped system, we can use this simple solution. And if we don't have a lumped system, we need to solve that complicated second order partial differential equation. Then the question is going to be, when we can assume our system is a lumped system. We know that, when we assume that the temperature in the solid is almost uniform. But how uniform? What about the center is 80? The surrounding, the surface is 75. What about if the surface is not 75, maybe 70? What about 65? What about 60 or 55? How much temperature difference we can say, okay, to be assumed to be lumped system? So to answer that, we can use what is called Beyond number, validation of lumped method. So when a solid is exposed to a fluid whose temperature is way lower, like standing outside in winter, you're losing heat. Are you a lumped system? Am I a lumped system? Not really. If I lump the system, my body temperature goes down dramatically. Then I'm going to be a dead body, right? I'm not a lumped system, so my heart is going to be at high temperature. I survive, right? Then how do we know, how uniform the surface and the temperature of the solid should be to be assumed to be lumped system? We can use Beyond number. That Beyond number can be calculated by this equation. Beyond number can be determined by convection heat transfer coefficient times characteristic length over thermal conductivity. In this case, the characteristic length can be determined by volume divided by its surface area. So when you calculate this Bion number, which is a dimensionless number, which means that it has no unit, when this value is less than 0.1, when this value is less than 0.1, then we say, oh, lumped method is fine. If the Bion number is greater than 0.1, then you cannot use lumped method and you go to approximate method to solve that transient heat conduction problem. That means whenever you see a transient heat conduction problem, the first thing you need to do is show the Bion number and confirm that whether it is a lumped system or not. So in your second exam, if you see a transient conduction problem, in other words, the temperature of the system changes in time, you need to show this is the Bion number. And because of the Bion number is this value, I'm going to use the lumped method, then solve it as a lumped method, or I'm going to use the approximate method and solve the problem in the approximate method. That section should be shown in your solution. Okay? You cannot just say, oh, I'm going to assume that this is a lumped system, then this is my solution. Then you will not get a full credit for that problem. Okay? Then there are a few things. So that's everything that you need to know in terms of how you can solve lumped system. Then there are a few things that you need to know, which is that the governing equation is again theta over theta I. In other words, T minus T infinite over Ti minus T infinite is E2 minus HA over rho VCT. And sometimes people like to say, many people like to, to simplify, especially for engineers. Some people like to say it's going to be E2 minus T over tau. And what is this tau? Tau is rho VC over HA. Actually, these are equal each other. And some people like to say this one is thermal time constant, which is shown here. And you can also calculate. So if you use this equation, you can determine what temperature of the solid at a time t. And when you study heat transfer, temperature is one. You may be interested in two properties. One is temperature. What is the other? The rate of heat transfer. Then how can we determine the rate of heat transfer? You can use this equation. The change in the heat transfer can be determined by rho VC times theta I, which is Ti minus T infinite, times minus 1 minus E2 minus T over thermal time constant. So these two equations, one for temperature, the other for heat transfer. Okay. So you can see total energy transfer, total heat transfer during time t. So these are the two equations, one for temperature, the other for heat transfer. When we go to convection heat transfer or fluid mechanics, many times we do dimensional analysis. So sometimes, the people like to use, the dimensionless numbers, like a Bion number. And this time in this chapter, I'm going to introduce a Fourier number. So B1 number is H, convection heat transfer coefficient times characteristic length. By the way, this characteristic length can be determined by volume divided by surface area and thermal conductivity. Fourier number is, on the other hand, alpha thermal diffusivity, which is K over density times specific heat, times T over characteristic length, which is this one, square. And by using these two numbers, you can simplify this governing equation. So this one, theta over theta I is T minus T infinite over Ti minus T infinite, can be also written as E2, not this one, minus B1 number times Fourier number. They are the same thing. Okay? So these are the three equations that you can use for the lumped system. That's all. Any question? That's the theory part of this lumped system analysis. Now we are going to solve a problem together to learn how to use these equations. Let me know if I go too fast or too slow. So we have a heat transfer coefficient. Oh, a heat transfer coefficient H. The heat transfer coefficient H for hydrogen flowing over a sphere is to be determined by observing the temperature time history. What does it mean? Temperature time history. The temperature is going to change with time, in time, right? So that means transient conduction problem. So that solid is made of copper and it's in a fluid which is hydrogen. So we have a tank of hydrogen, H2, and we have a solid in the middle that is made of copper. The diameter of this sphere is 20 millimeters. D is 20 millimeters, 0.02 meter. And the temperature of the copper initially, Ti initially 75 degrees Celsius. It's going to be inserted to the hydrogen. And we are going to calculate the heat transfer coefficient H if the temperature is 55 degrees Celsius when the time T is 97 seconds. So the surrounding fluid T infinite is 27 degrees Celsius. And the temperature of the solid T when time T is 97 seconds is 55 degrees Celsius. So let's calculate H. So how can we do that? Since we do not know how to do the approximate method, the only governing equation we know is going to be the lumped system analysis. So let's do that, solve it, and verify whether it is lumped system or not, right? We can do that. So what is the lumped system solution? This one. Theta over theta I. In other words, T minus T infinite over Ti minus T infinite is E2 minus HA over rho V CT. Then we know the temperature is going to be 55 degrees Celsius when time T is 97. So this temperature is going to be 55 degrees Celsius when time T is 97 seconds. What was the initial temperature? 75. So Ti is going to be 75 degrees Celsius. What is the surrounding hydrogen temperature? 27. 27. What is the density of copper? Copper density is, you can find it, or in your exam, I'm going to provide. Density is going to be 8,933 kilogram per cubic meters, 9 times heavier than water. And the volume, how can you determine the volume if you know the diameter? The volume can be determined by pi d cube divided by 6, where d is 0.02 meter. And specific heat of copper is, where are you? 384 joule per kilogram Kelvin, and H value is the unknown, and the surface area of a sphere can be determined by pi d square, and d is going to be 0.02 meter. So we have everything but H. Can you determine H? Yes, we can. If you do the calculation, H is going to be 63.5 watt per meter square Kelvin. So that's how you can determine H. However, that's not the end of the story. We used this lumped method. But there's no, the guarantee that you can use the lumped method or not. So you need to verify this is a lumped system. How can you do that? You need to calculate Bion number. That Bion number should be less than 0.1. If it is not, this answer is wrong, right? So let's calculate this Bion number. How do we calculate Bion number? Bion number is H times characteristic length L of C over thermal conductivity. So what is H? Oh, we just determined is 63.5. What is the thermal conductivity of copper? It's pretty high, almost 400 watt per meter Kelvin. What is the characteristic length? Do you know how to determine characteristic length? Yes, volume over surface area. Shown right here, volume over the surface area. So what is the volume? Pi d cube divided by 6. What is the area? Pi d square. So this is going to be d over 6, which is, do I have it? I don't have it. And the d is going to be 0.02 meter. Then you can determine Bion number. That Bion number should be 5.3 times 10 to negative 4, which is less than 0.1. So we can use the lumped system analysis. Yeah. The material property from a table, density, specific heat, K, they are material properties, will be provided in the exam. On the other hand, H is not. H is not a material property. It depends on the material and also the fluid motion. Okay, so the H should be determined every problem. That's what we are going to study later. in chapter 7, 8, and 9. Any question? Yes. Then you cannot use that equation. Yes. So that equation is only valid when beyond number is less than 0.1. Then you can use lumped system analysis. So when beyond number less than 0.1, that means that the temperature of the solid in time is going to be uniform in the solid. If the beyond number greater than 0.1, that means that there's a significant temperature, the gradient in the solid. Then the assumption for the lumped system is invalid, right? Because it's not uniform. So you can simply check whether it is uniform or the significant temperature gradient in the solid by using this beyond number. Pretty simple. Any question? Yes. Yes. So it will be provided in the exam. All the properties will be provided unless it is the one to be determined. So no more finding a property in a table in the second exam. I will provide everything. But please make sure that when there's a transient conduction problem, no matter what, if it is lumped system or approximate solution, always you need to show this is the beyond number. And show to me that the method that you are using is okay because of this beyond. So that's everything about lumped system analysis. Oh, let's solve one more problem because you look not very happy. This was supposed to be a homework assignment that I used, but I don't think that's going to be in your homework assignment. I'm going to solve it one more problem together. So we have a cereal is going to be cooked on this conveyor belt. I think there's a city somewhere in Michigan that's famous for, yeah, right? So this is a good problem, for us. Not really? Okay, so the thickness of this cereal is going to be 1.2 millimeters. So we have a solid, looks like this. And the thickness of this solid is going to be 1.2 millimeters. I don't like 1.2. It's going to be 0.0012 meter. Do not do unit conversion in your governing equation. Always convert all the units to whatever you're familiar with. Okay? Then the thermal conductivity and density and specific heat are available 700, 2400, 0.34. So I will provide those properties in the exam, like in this way. So each problem, there's all the properties will be provided at the end of the problem statement. So you don't have to look for properties. So we have density, specific heat, and thermal conductivity of what? This one. The product is to be baked by increasing its temperature from 20 degrees Celsius to 220 degrees Celsius. What does it mean? So anywhere in the cereal should be at least 220 degrees Celsius. Then it's cooked. Then where is your, where do you need to focus on? When you, determine that if it is cooked or not. The surface? Not really. At the center of this, the solid should be at the lowest temperature, right? So if the center of the solid is 220 degrees Celsius in the oven, away from the center should be greater than 220. So you can, you can ensure that this cereal is cooked when the center is 220. So our assumption is that the temperature of the center is going to be 220. This should be 220 degrees Celsius. What is the surrounding, the initial temperature? Initially, the cereal was room temperature 20. And now it's going to be in the oven, whose temperature is going to be 300 degrees Celsius. And convection heat transfer coefficient is 55 watt per meter square Kelvin. Pretty high to be in just, the quiet air. So you can say it's not just oven, it's a convection oven. So this fan is blowing air, increasing the velocity, trying to increase the AC value. And we want to determine the required conveyor velocity. What? What does it mean? Why do we need to calculate velocity? Is a dynamics class? No, not really. The length of this convection oven is going to be, and the conveyor belt is 3 meters. So if you know how long the cereal to be in the oven, then you can calculate the velocity, because the velocity is going to be distance over time. So the velocity is going to be 3 meters over how long it should be in the oven. So if you determine this time, then you determine the velocity. So it's not actually, the problem is not actually, to do any kind of dynamics analysis to determine the velocity. It asks you to determine how long it should be there in the oven to raise the temperature of the center to be 220. Once you get the time value, then you can use this equation to determine the velocity. So let's do that. So we know there's a change in temperature. The temperature of the cereal is going to increase from 20 to 220. So that's a dramatic increase. So the temperature of the cereal is increasing in time. So you can say, okay, this is a transient conduction problem. Okay, so it's a transient conduction problem. When you check that this is a transient conduction problem, what is the second step? There are 2 methods, lump, approximate. So we need to determine which one is what. So how can we do that? Let's calculate Biot number. How do we calculate Biot number? H times characteristic length over thermal conductivity. Then, how can you determine the, by the way, we know H value is given 55. We have K value given, where is it? 0.34, pretty low. And do we know the characteristic length? Not really. Can you determine that? Yes, there is an equation. Volume divided by area. Then what is the volume? I don't know. I only know the thickness. Then there is one way to determine this characteristic length. If you only know the thickness, assuming that this solid is extremely long, then the characteristic length is going to be half of the thickness. So in this case, characteristic length is going to be half of the thickness. So thickness divided by 2 is going to be the characteristic length. Okay? When you cannot determine V over area. Then what is the thickness? 0.0012. So what is the characteristic length? 0.0006 meter. Then can you determine the beyond number? Now, yes. What is the beyond number? That beyond number is, yeah, it's going to be small, 0.098. Very close. Very close, less than 0.1. Wow, almost, right? So if the value is less than 0.1, can you use the lumped method? Yes. Nice. So it's going to be lumped method. Then what is the solution for the lumped method? Theta over theta I is going to be t minus t infinite over ti minus t infinite is E2 minus HA over rho VCT. So initial temperature 20, surrounding temperature 300, surrounding temperature 300. What is the final temperature? 220, and density 700. Volume we don't know. Area we don't know, but we know volume over area, which is what? Characteristic length 0.006 meter. I'm sorry, 0.0006 meter. So A over V is going to be 1 over, this whole thing is going to be 1 over 0.0006 meter. And specific heat, 2400. Then, can you determine T? Yeah, you can determine T. So what is the time required? 23 seconds. Pretty fast. So if you leave this cereal in the oven 23 seconds, then it's going to be cooked. So what is the velocity? What is the velocity of this conveyor belt? The velocity is going to be the length of the oven, 3 meters, divided by the time, 23 seconds. So the minimum velocity you need to have is going to be 0.13 meter per second. That's how you solve this problem. Any question? Yes. HA over rho VC, and A over V is 1 over characteristic length. So characteristic length is 0.0006. So A over V is going to be 1 over 0.0006. That's what you can do. The heat transfer analysis. Now you are an engineer. What do you want to do if you're working for this company? If you're working in, what was the city? Battlefield. No, Battle Creek. And working for, what is the name of the company? Okay. I thought that they have 2. No, just 1? Oh, okay. I didn't know that. Then why you only say Carol? There should be another one. What is the other one? You don't know? Okay. So you're working for that company as a mechanical engineer. What do you want to do? What do you want to do? What do we want to do as an engineer? We want to improve. We want to improve what? The productivity. How can you improve the productivity? You need to cook those cereal faster. Then you need to increase the velocity of the conveyor belt, right? Then you can, manufacture this cereal, faster to save money, right? Then how can you make it faster? You can make it thin, so that the time required to increase the temperature of the center of the cereal to 220 can be shorter. So we are going to propose, I'm going to propose, not me, an engineer suggests that if the flake thickness is reduced to only 1 millimeter, of course it's going to change the taste. As an engineer, I don't care. That's the marketing department, right? So if you make it thin, then let's see how much velocity we can increase. So we are going to do this whole analysis one more time. So this time the thickness is going to be 0.0005. I mean the half of the thickness. So this time solution suggestion. Now characteristic length is going to be 0.0005 meter. Let's see what's going to happen. When you change this property, then you need to recalculate Biot number to make sure that your steel has lumped system. So Biot number can be determined by H times L of C over thermal conductivity. And H is going to be 55, thermal conductivity is 0.34, and L of C is going to be 0.0005. Then what is the Biot number? What is the Biot number? I don't have it. Can you calculate that? So it's going to be 55 times 0.0005 divided by 0.34. Now the Biot number is going to be 0.081. 0.081. Still less than 0.1. Nice. So we have a lumped system. Isn't it nice? When you solve a transient conduction problem, if you see the Biot number is greater than 0.1, you won't be happy when we go to approximate solution, okay? I'm pretty sure that you won't be happy. So complicated, okay? So anyway, now we know it's a lumped system. So let's use the same equation. Theta over theta I is going to be T minus T infinite over Ti minus T infinite is going to be E2 minus HA over rho VCT. What is the temperature? 220, surrounding temperature 300, initial temperature 20, surrounding temperature 300, H55, area over volume is the 1 over characteristic length, which is 1 over 0.0005. Density, what was it? 700, and specific heat 2400. Can you determine time T? Yes. Now it is only 19. So previously, the cereal should be in the oven for 23 seconds. Now only 19 seconds. So how much, how much more cereal you can make? At least approximately 25%, right? Which is good, isn't it? So what is the velocity of the conveyor belt? Now the velocity is going to be x over time. The length of the oven is 3 meters. How long it should be there? 19 seconds. So what is the velocity? 0.16 meter per second. So we can increase the velocity from 0.13, 0.16. So what's going to happen? The company is going to get more money, and the guy who is packing this cereal box is going to be bad because the velocity has been increased, right? So that's everything about lumped system analysis. Any question? Yes. A Biot number should be less than 0.1. That is, where is it? Oh, where is it? Oh, oops. That's interesting. It is missing. It should be somewhere here. Biot number should be seriously, it's gone. Okay, so let me write it for you. So Biot number, which can be determined by HL over K, should be less than 0.1 to be lumped system. If it is greater than 0.1, then you cannot use lumped system anymore. You have to use this approximate solution that we are going to study now in the next 5 minutes. Okay? Yeah. So whenever you see a transient heat conduction problem, show this one. If you don't show that, you will get minus some numbers. That's case by case. I will make sure that that won't be 0.1 in your exam. But usually, I think that's okay. You can use beyond. You can use lumped system analysis. But it is very unlike you see exact 0.1. Yes. Like, what's the range for? That is shown here. So the question is whether there is a temperature distribution in the solid or not, right? So that means the conduction resistance is great and convection resistance is low. So the conduction place dominates the heat transfer. Then there is a temperature gradient in the solid. So when Biot number is less, that means that conduction resistance is pretty small, so you can neglect that. Then the only, the dominate heat transfer is going to be convection. So that was the justification to use a Biot number. I have a slide to show that. I just cannot find it right here. So internal heat flow, that's conduction. The conduction resistance is small. In other words, Biot number is small. You can neglect temperature gradient in the solid. That is the, the bottom line to use lumped system. Make sense? Okay. That's all. Not for today. We have 3 minutes. So let me give you a summary. So there are 5 items to be in your first exam. Sorry, second exam. I don't have a copy. I need a copy. This Pepsi, no, not Pepsi, doesn't have me. So there are 5 items. You will see 3 or 4 problems among these 5. And there are 3 items from chapter 3. Q is delta T over the sum of R. You remember that. That's the first item. The second item is when we have a heat generation in the solid. You remember that. Right? That's the second item. The third item is going to be when we have a fin. So you already studied all 3. Fourth item is going to be when Biot number is less than 1, lumped system. So you already studied 4 items out of 5. So the last one is going to be the approximate solution. So you will see 3 or 4 problems among them in your second exam. Anyway, we have 2 minutes. I can finish that. Just give me time. So in reality, if you cannot assume lumped system, that means you have a significant temperature gradient, right? You have a significant temperature gradient in the solid. So you cannot neglect the left-hand side of this heat equation. So the left-hand side, you have a partial differential equation, second order. That means you need to have 2 boundary conditions. And right-hand side, you have a time derivative. So how many variables to determine time t and temperature t? X, location, time t, initial temperature, surrounding fluid temperature, the size of the solid, and the material properties, and the convection heat transfer coefficient. So how many variables? 1, 2, 3, 4, 5, 6, 7, 8. Are you happy with them? No, I'm not happy. So, can we solve it? Yes. No, we can solve it. We can solve it. How? We have those genius in the Pierce Hall. Who are they? Yeah, math. The people in math solved this problem surprisingly, okay? Not surprisingly, they can do that. So instead of solving that equation as is, they use a dimensional analysis. So instead of t infinite, ti, they just use one variable, which is theta star. That theta star is t minus t infinite over ti minus t infinite. So three variables become one variable. And instead of the x and x, they use x star. So two variables become one variable, like a magic. And they combined alpha, the thermal diffusivity, time t, and the characteristic length into one that is a Fourier number. So 8 variables reduced down to only 3 variables. And then, using 3 variables, now we can solve it. And the process, 1 minute, over. So the process, we are not going to study that because we are not majoring mathematics. So this is the solution. So this is what we are going to use. However, you are not going to use this equation as is because it's very complicated. So on Thursday, we are going to study how to simplify this equation that is called the first term approximation. And I think we can finish this section by Thursday. So your second exam is going to be next Thursday. What? No, next Thursday is not Thanksgiving. The week before Thanksgiving. Next week. Yeah. So next week. Oh, all right. So if we finish on Tuesday next week, your second exam is going to be on Tuesday in the week of Thanksgiving. No? Okay. So here. Okay. Give me 1 minute. 1 minute. So let's. I'm going to stop this one. Okay. 1 minute. If you want, I can move